Okay, so next we will build our continuum model for one-dimensional convolution to be used later in deconvolution. So I think first let's build our point spread function. Related to disk shape. Maybe this is so weirdly said, let's put it in quotes. So result should be function. Let's do this as a function. Let's call this our, let's call it the PSF for point spread function, and in comes x. So so x is a real number. I think we could have the a. It's kind of a question what to do with the a parameter giving the width. Let's start in a simple way, having it just here. Maybe in one sense it would be good to have that as an argument too, but I'm not sure. It depends on what happens next. Is it a good idea or not? We'll see. We can change it later, I guess. So this would be the value of the function at that point. And maybe let's just define it here. PSFX is c times square root of a square minus x square, where c equals 2 over, I think, pi times a square, maybe something like this. Let's see. I will steal these to be used down here. So a, let's first make it like 0.1. Okay, and then we need an index for x points in the interval from minus a to a. In the interval from minus a to a, because outside that it will be 0, and inside it will be defined by this square root formula. So index is absolute value of x is smaller than a. That's an index, and maybe we can also here we can initialize the result. So result initialize as zeros, then we get the points outside that interval will be automatically then zeros. So this was zeros of size x, like this, and then evaluate PSF for x values in. So then, and also maybe we can just make the normalization constant already. Nope, like this. Index, and then here result equals this. Okay, so we're almost done. There is one error in this line. Can someone catch the error? Haha! I said you have to think. Okay.
I didn't even think, but it's usually if you see those hats there.
Yes.
There should be some point at some.
Exactly. Because X may be a matrix or vector. It could be a square matrix even. Then this would mean the matrix times itself. That's not what we want. We want element-wise square.
But you also need to take the indexes.
Yes. Oh, there were two errors. The other one I didn't even realize. Great. Extreme programming. Not in pairs even, but I don't know how many are we, 30 or something. Highly extreme programming. Okay. Let's try this. Where did I save it actually? Let's save it again. Yeah, this is in a wrong place. Let's save it to our course. So now actually I started a folder Matlab, and there we have deconv of this year. There are previous versions as well on the previous course web pages. So now we have this, and actually we could also let's make a plot. Take a look at the PSF. Okay, figure, and then evaluation points. Let's put from x linspace from minus, let's put minus half, minus 0.3 to 0.3, for example, and let's have 100 points, and then plot x and PSF x. Let's see what happens with this. Oh, we have to save, so let's call this PSF plot, and we should save it. Here. Why? This is very weird. Of course, yes. Sorry. So here still something strange in here. So this should be only result at the index points. So the points for x in that interval. Debugging. So here is our point spread function. It is 0 outside the interval from minus a to a, and inside it takes this form, and now I think it's supposed to integrate to 1, hopefully with our normalization. We'll see later how it works. So anyway, now we can evaluate our point spread function at any real point. Some progress, that is. Okay, and then let's build our target function. Let's call it. Yes.
Showing what the index is on that picture that you drawn on the board, because I'm not sure. I mean, I understand that the index is defined as the values between negative 0.1 and 0.1.
Okay, let's take a look at the index thingy. Where is our? So actually, let's take here some x equals linspace from, let's say, from minus 0.3 to 0.3, and let's take 15 values. So then we have an x like that, or let's make it a vertical vector so we can more easily see it. So here we have such x points, and now if we make the index trick that we have here, so this index for x in that interval, so let's see how that looks like. Okay, so this is what the index is. Index vector, the vector has the same size than x, and it has a 0 for points outside the interval and a 1 for points inside. So it's just for picking out values in vectors. So that's why when we do it here, so we are only changing the values of the result for those center points, and because we use x here, also this formula here will give a number only for as many values that are in x vector inside the interval. Okay. It's quite a useful construct in Matlab. So then construction of a target function to be reconstructed. And again, let's do a function. Result equals, let's call it target f. Any better name? What do you think we should call this? Well, if you invent a better name, let's change it. But now let's save it as target f there, and maybe if we take from here okay, and now let's again initialize as 0. So result is zeros size x. And then let's build a few features into the function. We can change them later if we want, but let's anyway put a few discontinuous spikes into it. And again, let's do it with the index. Index 1 is for, let's say, x is bigger than 0.2 and x is smaller than 0.25, like this, and then result at the point index 1 equals 1, say. And let's take a plot of this one. View left, right. Here. So let's save this as target f plot. So now we actually want evaluation points in the interval from 0 to 1, that's where we will be working with our convolution and deconvolution problem. And now, kind of wanting to avoid any boundary condition issues, let's just design our target f so that near the endpoints of the interval it will just be 0. So for simplicity. But here let's plot our function in the interval from 0 to 1, and let's have quite many points. And here target f, and we could even have a little bit wider line for it. Okay, so let's see how it looks. Okay, so what we have now is just one spike like that. So I think let's add a couple of more, maybe one narrow and one a bit wider than this one, to have a few discontinuities. So let's have index number 2, and now this would be, let's say, x more than 0.28, but less than 3, and let's put this to, here, this should be 2. 1.2 to be a little bit of different height. So let's see how it looks now. So now we have a bit more narrow one, and then we could have a third one a bit wider. So maybe let's say from 35 to 45 and 0.7 value there. Such a thing, and then let's include something that's kind of smooth and continuous in some interval. Oh no, please just close, and then smooth feature. So let's have an index 4. Let's say x is more than 0.6 but less than 0.85 to keep this interval of 0 values also near the endpoint 1 of the interval. And here let's use, let's say, sine of x index 4, but maybe put a bit more rapid oscillation. Let's see how this looks like, for example. Maybe we could have even a slightly bit more rapid oscillation. Let's put here 20 and see how it looks like. Maybe a bit more. 25. So now we have this kind of several different discontinuities and then some interval of quite smooth behavior. Let's go with this first, and later if we want to modify it, we can of course always do it. So next we would need to compute the convolution. And I think in the interest of later quick evaluation of the convolution result, I'm thinking of doing so that let's first compute the convolution function in, let's say, 2000 points or so in the interval from 0 to 1. Do that in a for loop, compute it quite accurately, then just save the results, the points and the values, and make a little function that will just interpolate from those values. So then later when we want to just evaluate the convolution, we don't need to compute any integrals. We can just interpolate from previously computed values. This will be quite a fast thing to do. Did this make any sense?
So this is for the specific PSF.
Yes, for a specific PSF with a specific A value and for this particular target. So if we change anything, if we change A or PSF or anything, then we have to recompute our target, because then once we have this quick evaluation function for the convolution result, we can easily evaluate the continuum model points in that vector without then doing any numerical integration or stuff. Just it will be such a smooth function that with fine enough sampling and, let's say, spline interpolation between them, we will get quite accurate enough values for it. Okay, I hope this made sense. If not, let's go through this and see how understandable it becomes. And now I think this file I will already name now. The construction of continuum model measurement data. Let's say simulation of continuum model measurement data. And here we evaluate the desired convolution between functions of a real variable at quite many points, and save the result to a mat file. Then later evaluation can be done quickly by interpolation. Okay, and let's call this, for example, deco 01. So we'll be building a series of functions numbered like that for the deconvolution problem. Let's call this cont model comp. So here, let's say choose many evaluation points. So let's say X is lin space from 0 to 1. Let's put there 2000 points, for example. Well, let's first put only 20 and later increase the number. And then in each point, we should compute the value of the integral. Actually, at this point, we could we need this A. So there's a little debugging risk here, whether we use the same A here than with the PSF. Maybe we could send it as a parameter. I think it's probably better to do it so that at the PSF we have here A is the width parameter. PSF is non-zero, is 0 outside minus AA. And let's take it in here and remove it here. And when we plot our PSF, let's here also have the A. Okay, I think it's better this way. And then we need to integrate. We need to integrate from minus A to A. Integration points for the interval minus A to A, and let's do it. Now there are many choices we could use. The midpoint rule is the most simple one, and then we could do trapezoidal rule or Simpson or Gaussian integration or whatever. Let's just do it with a very simple midpoint rule. It's very simplistic, but let's not mind. So y is the integration variable, and let it be Lin space from minus A to A and ny points. Let's put here ny equals 128, for example. Then let's compute delta y, which is the difference between consecutive grid points here. So it will be y2 minus y1. Then evaluate the integrand, the function to be integrated. So the integrand is the PSF at points y, then pointwise multiplication with our target f function. Target f function, we should do it in x minus y. But what is x now, actually? X is actually a vector of points, and we want to evaluate at every point. So we could initialize the result. Result of convolution is zeros of size x vec, like this, and then we should loop over x values. One to length x vec with the current x. So actually here we should have x vec, or maybe we can actually even do x equals x vec. Yes, and here is x minus y. And then compute the integral. And with the midpoint rule, we just so the convres at this point should be the width of the base of the rectangle times the height. So this would be int I think it should be okay. Let's see. And here I usually like to put all the data that we produce into a subfolder called data. Sometimes it confuses people when there is no data folder, so let's just avoid that problem by making the directory here. However, then after the directory has been created once, then every next time when you run this, it will give a warning that the directory already exists. It doesn't matter at all. The warning is just fine. But in my experience, several students every year get very confused because there is no data folder. And let's do it this way. Maybe this is less confusing. I don't know. But anyway, now let's save x, and let's save also a, the width parameter, and then the convres to a file. Let's call it conv.data, for example. Let's see if this works. Oh, it doesn't. PSF, yeah, we should evaluate PSF including the width parameter. Okay, and here we need this one, and then let's, just for the fun of it, let's plot x and convres. Oh, there is nothing. Why? Why is there nothing in the picture? Come on. Maybe this is a great spot to have the break. Let's continue 15 past, so 10 minutes break.